I'm just, there you go.
Okay, Jeff, if there's time at the end, I'd like to just talk about what's up in the coming week, and especially talking about the Venus-Saturn conjunction on Sunday.
Yep, go ahead.
No, at the end.
Oh, you want that at the end? Okay.
Yeah, so if there's time after our speaker and Jim, who are.
Perfect. Is there anybody else who has anything else that they want to ensure we try to get on the schedule tonight? Okay. We'll give it maybe 2 more minutes for people to come. Okay, Chris, are you okay if we get started now?
Yeah, please do.
Yeah, super. So welcome everybody to the Astronomy Cafe. The first one starting at 7 o'clock on January the 16th. We've got an interesting program today. Our speaker today agreed to speak with us through the efforts of Marjorie Welshframe, and also Dave Payne. But tonight was the best night for her presentation, so I have the privilege of introducing her. She is currently the astronomer in residence at the Canada-France-Hawaii telescope, which is the 3.6 meter scope, which is both optical and infrared, on Mauna Kea. She has an Inuit background, family from Saguenay, Lac Saint Jean area of Quebec. Graduated from with her PhD from Laval University in 2017. With that, she becomes the first Indigenous woman in Canada to obtain a PhD in astrophysics, which is kind of cool. She then did postdoc work at University of Hawaii and is now the astronomy in residence at the Canada-France-Hawaii telescope. She is also the principal investigator for the SIGNALS program there. And SIGNALS, as I'm sure you're interested, stands for Star Formation, Ionized Gas, and Nebular Abundances Legacy Survey. Actually, your scope and your area has about a 3-page list of acronyms for the various programs. So it's quite interesting reading through that. This survey, the SIGNALS program, is aimed at observing thousands of star-forming regions in nearby galaxies. So I'm delighted that she's agreed to speak with us tonight. So this is Laurie Rousseau-Nepton. Okay, Laurie, it's all yours.
Thanks, Jeff, and thanks for inviting me. I'm very pleased to be with you guys for about an hour, talking about my job, my programs, and a little bit of science and instrumentation. So I'll just start sharing my screen. I am very visual, and I have a lot of pictures and videos for you guys tonight. So here you go. By now, you should see my first slide.
It's good.
Perfect. So I am a resident astronomer at the Canada-France-Hawaii telescope. I've been here for 6 years now. And as a resident astronomer, my job is to make sure astronomers and students around the world can use this telescope efficiently. I am specialized with one of the instruments that is installed on the telescope. And I'm going to talk a little bit about that instrument called CITEL. But our telescope has 5 instruments. Just to give you an overview, it has very large imagers, one that is for the visible megacam, and one for the infrared WIRCam. And then we have 2 high-resolution spectrographs, which are looking at one star at a time. One for the visible espadons and one for the infrared Spirou. And they are both polarimeters, so they can look at polarization of the light as well for those stars. And then finally, CITEL is the one that does both. It's like both an imager and a spectrograph. So the data is very different, contains a lot of information. And that's what I use for my program. So I started this whole journey at the Montmorency Observatory. As a student, I used this telescope to test an instrument that was called Espion. And I was spending a lot of time observing. So throughout my master and PhD, back in those days, if I put all of those observing run together, I almost spent a year at the observatory making this prototype instrument working. And I was doing that under the supervision of Carmel Robert at Laval University. And Espion looks like this. So it's a prototype. So there's a little bit of tape on it, like any good prototype. And a few instruments, a few students were working on the instrument to make sure it was working properly and that we could actually do science with it. And Espion was the first spectral imager, like CITEL. We call them Fourier transform spectrograph. And I'm going to talk a little bit more about that later. But that's the way Espion look. And that's a picture of me right here on the right, and on the second on the right. And I was with students back then. I was training students to use the telescope, to use different instruments at Montmorency Observatory. And with this expertise, this is how I got hired to Hawaii. So from Espion came the idea of building CITEL for Hawaii. And Espion is an instrument for which the PI, the principal investigator, is Laurent Tristan at Laval University, which is the husband of Carmel Robert, my supervisor. So we had this team, basically, of students both working in instrumentation and science around building instruments for telescopes. And that's a picture of the group with me at the center here. So when CITEL started, it was in 2010. So it takes a while to build an instrument and make it work for a different telescope, a larger one. This is a picture of CITEL in the offices of ABB Bowman in Quebec. It's a company that was working with Laval University to build the instrument. And the engineer that was in charge of the project is Julie Mandar. She's right here on the image. And then she worked on the instrument and made sure that it would be good to work on the Mauna Kea. And by that, I mean, the Mauna Kea, the CFHT, the Canada-France Hawaii Telescope, is operated remotely. We cannot be there during the observations. So the instrument has to work on its own. There cannot be anyone interacting with it during the night. So it was a very important part of the design. We needed an instrument that was really independent. And what it does, so why do we want to build those instruments that are so different, those Fourier transform spectrograph, is because we want to see spectra. We want to see the light in all of its components. And I like this periodic table here. It's the periodic table of spectra. So each element in space have their own signature, their own fingerprint in light. And so if you look at the spectra of hydrogen, you have some specific colors that come out, and each of those atoms have different signatures. So by doing spectroscopy, you can identify the presence of those atoms in space, which is very convenient if you want to know what matter is made out of and what stars are made out of. And so depending on what you're looking at, if you're looking at a star, this is like just a little overview of like a telescope looking at a star, like you might be able to see the full rainbow of colors. If you're looking at, if you have a telescope that is looking at a nebulae, just gas in space, then you'll see those signature, because gas, the warm gas emits different colors depending on what is inside that gas, what kind of atoms. And of course, sometimes we have a combination of the two when you have something very hot, like a star, and its atmosphere, which is gas, then you'll see absorption spectrum. So you'll see the rainbow, and then there will be some lines missing from that cooler gas that is around a star, for instance. And of course, we can study different kinds of stars with their spectra. So it's very, very convenient. But like I was mentioning earlier, most of the time, you use a telescope, you use a spectrograph, you're looking at one star at a time, and you get one spectrum. So the beauty of building those instruments, Espion and CITEL, is to gather a lot of spectra at the same time. And ultimately, when you look at an image, like the one behind me, I selected it on purpose. So my background is an image from CITEL. Each pixel of the image is ultimately a spectrum. And you can just get that pixel and get the light coming from that area of the galaxy and see what is composed of that light. So what is inside the galaxy. So those are exciting pictures. That's me back in those days when CITEL was about to get ready to be sent to the Mauna Kea. We had to test it, to cold test it. So to test it for the environment at the summit, which can be about -5 to -10 degrees at night. So we use civil engineer, a gigantic refrigerator that we have in the civil engineering department at the University of Laval. And we bring the instrument in there with huge compressor, lots of vibration, very different than an environment around the telescope, but we would be able to cool it down to those temperature and test it, make sure the optics was well aligned and that everything was working fine. And right after that, we shipped the instrument to Hawaii in a plane, crossed our fingers that everything was going to go well. And we took a plane to follow it. And we had 1 week to do the test on sky. And during that week, we were pretty scared that this hurricane called Guillermo back in those days was going to hit the island. But fortunately, it just got, it decided to go north at the very last moment, and the island was safe, and we got 7 beautiful nights to test the instrument. And so that's a picture of Guillermo not going to the island. and that is ultimately the first image that came out of CITEL. So this is M57. It's a planetary nebulae. You might recognize it more if I do an image like this. But what I was interested in was this tiny galaxies and this one in the back. And within the first night, I could get the data, analyze it, and that's what I was doing in my computer right there. And I could get abundances, so what is in that galaxy, what the gas in that galaxy is made out of. Astronomers, we call that metallicity. So everything that is not hydrogen, like literally all the other atoms that are not hydrogen, are put together in a bunch, and we compare their amount to the amount of hydrogen, and we call that metallicity. So there's more metals, all of the other atoms in the center of the galaxy, where there's more stars that fabricate those atoms. And there's less of them in the surrounding of the galaxy. It's like a slow process of building up heavier elements. And of course, since we have spectra, we also can see the Doppler effect. So if the signature of those atoms moves to the blue or to the red, it tells you about their speed. And so you can extract the information about the rotation of the galaxy. So pretty cool. And I graduated right after that. So that's a picture of my graduation with my fellow PhD students and my PhD advisor, Carmel Robert. So I was sent to Hawaii with the instrument. Ultimately, there was a position that got open at the Canada-France-Hawaii telescope right after that. And since I was an expert with CITEL, I was hired to help people use the instrument. So this is the Big Island of Hawaii. I am located in this area right now. This is where I am on the west coast, where our headquarters is in Waimea up here, and the Mauna Kea is right there, not too far. And so the island of Hawaii is an island that is there's active volcanoes. You might have heard of it in the news, but it is something that we have to deal with while observing. So volcanoes means volcanic ashes, volcanic gas, and also earthquakes that can interfere with observation. And this is a picture of the crater that was in 2021, but more lately we got an eruption on the Mauna Loa right beside it. This is a picture from one of my friends. And this is a picture from the lava lake on the Kilauea volcano yesterday from a friend of mine. But on the Mauna Kea in the winter, and actually right now there's still a little bit of snow, so this image is kind of accurate. We have snow during the winter, and what I like also about that picture, and you can see it very well, is that inversion layer where most of the clouds forms is usually below the summit. So when you drive up you cross the clouds, you get up to the science reserve there where the telescopes are located. And as a result, we get many, many clear nights through the year. This is a picture during the summer from another point of view, from the Mauna Loa. This is an aerial view of the summit. And if I zoom in to the very summit where we have the science reserve, you have the facilities that are installed at the summit. CFHT is at the very end of the road right here. There's this big loop that goes around. And if we have a closer view here is CFHT. Beside Gemini, UH, UCURT, IRTF, and Keck, not too far away. And we do have storms, even though we're above that inversion layers and lightnings. And this short video, I don't know if you saw it, but there was lightning falling on Gemini. And Gemini is connected with us with a beautiful optical cable. I think we can see it, yeah, here. There's a pipe that connects the Gemini telescope with us. So we can use this 8-meter class telescope to feed our spectrograph Espadon. So some astronomers around the world, they need more light to observe their star, but we can convey that light from that larger telescope into our instrument. So that's also a pretty cool aspect of these two telescopes together. Okay, now CFHT with this magnificent dome, the dome vents. If we get inside, this is what the telescope looked like from above. There's a rose that protects the mirror during the day, but eventually it opens to let the light go in. There's some people here to help you scale the size of it. I have a short video that shows how everything moves. So at around sunset, we have the dome slit opening, takes about 2 minutes. On this image, we have MegaCam installed at the upper end of the telescope. So both the imager are installed on the upper end of the telescope here. They have very wide field of view. So when we use all the spectrograph, we put a secondary mirror there, and the spectrograph are installed under the telescope. You'll see the rotation of the dome in a few seconds, and eventually the telescope is also going to tilt towards us so we can have a glimpse on the mirror. There is no sound, but believe me, it's very noisy, especially when the dome is rotating. The telescope motion is pretty quiet, but the dome rotation is pretty intense. So now I wanted to introduce a few things before talking about my science. So just to give an overview of why I'm studying star formation and why we're doing signal, and how it is all intertwined with the instrumentation that I am developing. So since the Big Bang, everything has changed from a universe that was pretty simple, made out of very small particles. After the Big Bang, formation of the first atoms, mostly hydrogen, helium, a little bit of lithium. And then ultimately, what changed things is the first stars that formed through a gravitational collapse. And those first stars, they were really different than the stars we know today. There are many evidence of that through many studies nowadays. Those stars were known to reach more mass, much more larger mass than the one we have today, like 1,000 times the solar mass. But ultimately, all of those first stars contributed to fabricating new atoms, heavier atoms that we now have in the periodic table. And they changed galaxies. They changed the universe chemical composition, and galaxy grew in the same time those first stars were forming. So at the same time we had this formation of the first stars and the first pre-galaxies, galaxies were merging, forming larger and larger galaxies. And in this video, what is kind of green is the gas, what is kind of blue are the newborn stars, the young stars. And as time goes, we have that kind of reddish color that represents the older stars that are more concentrated in center of galaxies, but not always. And ultimately, we form galaxies that are much more organized, like the spiral, like the Milky Way. Disk galaxies that are forming stars, but contains lots of gas and lots of older stars. But those first galaxies, they were more like small, irregular, forming a lot of stars, having a lot of massive stars inside of them. And this process of fabricating new elements through the formation of those massive stars was really important. So now we have this universe with all these galaxies and all these kinds of different morphologies of galaxies. And some of them form more stars. Some contain more older stars and are more passive, like the elliptical galaxies are mostly passive. They don't form as many stars. And we have the irregular that are like smaller, that are lookalike of those earlier galaxies from the early universe. And of course, we have some stragglers or outlier here that have very weird shapes due to interaction with other galaxies and things like that. And inside galaxies, we have those little blobs that are often seen in red in like HST images, the star-forming regions. So if you focus on those little red blobs in galaxies, and I have this very nice video here that's going to show you a simulation of star formation. So it's a cloud, it's a perfectly spherical cloud of gas. And as I'm going to press this button, it's going to evolve through small perturbation, gravity, and ultimately form stars and that more denser filaments that are kind of yellow in here. And in a cloud like that, that is about 100 light year across, so it's a pretty big cloud, you can form hundreds, thousands, tens of thousands stars that are a little bit like sisters because they are made out of the same material, but they are different because they don't have the same mass. Some are more massive, like 100 times the mass of the sun nowadays. Some are just like the sun, and some are smaller, of course. A lot of them are smaller. So it basically forms these beautiful clusters of stars. And they're sisters, but within like 100 million years, they're going to dissolve in a galaxy. They're going to get disrupted, and eventually a young stellar cluster like this will start to lose members, and you won't be able to recognize it a little bit later in time. So when they're really young, a couple of million years, there's another thing that is important. They're still together, but they also still contain the very massive stars that were formed through them. So the very massive ones that are 20 times up to 100 times the mass of the sun, they are very important because those are the ones that produce a lot of light, a lot of very energetic light. And it is energetic enough to heat up the gas surrounding the star-forming region, and it starts to glow. So the beautiful ionized nebula, warm of gas around those stars is only there for a couple of million years while those very massive stars are there burning. And eventually they will explode in supernovae, and this beautiful bright nebula that is shining will also disappear with them. There's a lot of simulation that also simulate heavier stars, like formation of really, really heavy stars. This is just another example of a simulation, and it simulates something that is a little bit closer to an area that you might recognize here. So this is the Tarantula Nebulae. It contains the two of the most massive stars we know of, and they are close to 150 solar masses, if I recall, from their last estimates. So that's pretty interesting. We have those clusters of stars that form sometimes 10, sometimes thousands of stars. And then we have this distribution of mass, a few very massive ones and a lot of low mass star. And we call this mass distribution the stellar initial mass function. So it is still debating, we're still debating that in astronomy, if that function is stable through the age of the universe. Were stars always forming like that? And what was that distribution before? And is it true in every corner of the current universe? Our stars are all forming like this. Another periodic table that I like to show is this one. So the origin of the elements from astronomical phenomenon. So of course, the Big Bang, as I mentioned, you have hydrogen and helium, a little bit of lithium. And then you have other things, maybe a little bit more eclectic, the cosmic ray fission here. But mostly the important ones that I want to show here is the exploding massive stars in green. So everything that you see here in green, which is pretty important, is coming from those massive stars exploding. So I'm focusing on that a little bit today, and you'll understand why. Because massive stars, they are lighting up the gas. They're producing these big bubbles of warm gas that we can see from very, very far distances. And this is a simulation showing a bubble of warm gas produced by a B star. And this is a O star, slightly low, like higher mass. So those bubbles are created pretty quickly. And about 100,000 years, it is created and it is stable with the amount of light coming from the star and the gas around it. And this is real images of those nebulae. They're often called H2 region, H2 for ionized hydrogen or warm hydrogen. So a star forming region, you have a couple of ingredients there that are important: the stars, the gas, the warm gas around it. And so what I study is the characteristic of the stars. So what kind of stars do we have in the center? Mostly the OB massive stars. What kind of photons they're producing? How much gas do I have around them? What is the gas abundances? What this gas is made out of? With a different spectral signature that I can detect with the spectra. And also the free electrons, because within that, the free electrons are really important. So what is happening is that you have those high energy photons that are swimming around in that gas, and they're kicking atoms and they're kicking out some of their electrons. And that's how you get those warm gas, those ionized gas. And those free electrons are just bouncing around, and they collide with themselves and with atoms, but mostly with atoms and ions. And they are responsible for a lot of the light that is produced by the nebulae. So if I want to really simulate well what I see through my spectra, through my telescope, I need to simulate well the condition in those electrons population. Okay. And of course, again, when you're thinking about those photons coming from the stars, you have photons from all colors like the rainbow. But when you're thinking about the colors coming from the gas, it is specific colors, a specific signature, something that you can very easily identify. Okay, so I was picking that little region earlier to start to talk about the star formation process, but it is evolving. So this little video here show a rotation of a spiral galaxy, and all these little red bumps that appears and disappears are star forming region. This is really accelerated, of course, but within billions of years, you have these regions that appears constantly and disappear when the massive stars explode. And they last up to 40 million years when the stars have been formed. Depending on what kind of stars are in there. So you might know some very well-characterized star-forming region like Orion, which is actually an ultra-compact H2 region, ultra-small star-forming region compared to what we see in galaxies. This is an image of an irregular galaxy called NGC 6822. You have this big guy over there that is 100 parsec. So it's 25 times as big as Orion. And some are like 20 parsec, others are about 10 parsec, and little blobs here about 2 parsec. So you have a wide variety of sizes in star forming regions. And just remember that big guy here, because it's like a perfect circle. It's about 100 parsec, 25 times Orion. It's a good thing to keep in mind, because I'm going to show you other objects here. Here you have NGC 2403, which has large complexes of star forming region. This is 1 kiloparsec, so 1,000 parsec here. You have another region here that would be about the size of our 100 parsec region. And if we go on another galaxy that is farther away, so NGC 628 or M74, if we go a little bit farther, because this one is at 9 megaparsec away from us, then a region like this is about 1 kiloparsec in size. And if we wanted to detect a region like the one I just showed you in that galaxy, it would be very hard. You can see thousands of them here that are identified through coding. But ultimately, if I zoom in into that red square and I look into all of these areas that are warm gas, this thing would be about the size of our spherical region of 100 parsec. It's barely, you can't barely see it on the image. If I would put that region at the distance of this galaxy, it would be, well, Orion, and this region would be about a pixel in size. And Orion, you would not detect it. You would not even see it. It's too faint to be detected at that distance. So it gives you an idea of the kind of big guys that you can find in star forming regions and the smaller one. So studying them is important. They are the way our universe gets transformed. But it's also complex. I don't want to say you just have to look at the regions you have around you and study them and understand what's going on. There are some tricky part to doing these observations, out of which you have stars that are all over the place in galaxies. So the H2 region, the warm gas, is actually floating and surrounded by stars. It's surrounded by dust, which blocks some of the light. And also you have little diffuse filaments of gas that can contaminate your data when you're studying that. And then ultimately, if you look at a cloud of gas, it might look uniform, like a perfect sphere, but it is not. And so you have denser areas that have like molecules and other stuff. You have areas that have different temperatures, cold, warm, hot. And stars are located somewhere in there. And the gas density can be different. Its composition can be different. So there's a lot of things that get involved. And stars inside those regions, they can be warm, more warm, or even more warm, like depending on their mass, if they're more and more massive. So you need to know what kind of mass those stars are to understand how much light they produce and things like that. So that's the challenge in what I'm doing, understanding each of those regions, trying to study them, understand the characteristics of the stars and how they eventually return to the interstellar medium, to the gas, new elements, and transform galaxies. So yeah, so that's how it comes to place. So that's where I use CITEL. Why do I use this beautiful instrument that is installed at the Canada-France Hawaii telescope? This is a drawing of all the CITEL's part. It contains a very important part right here in the center, which is called an interferometer. And I'm going to show you very quickly how it works, because I think it's pretty cool. So this is a few pictures of CITEL in the lab, in the dome, and this is the team that is in charge of installing the instrument under the telescope when we need it on. And on this image here, you can see CITEL under the telescope behind us. So the heart of CITEL is an interferometer. So what is an interferometer? This is a Michelson interferometer. This is a simple interferometer where you have a light source, so you can think about a laser or something shining into the interferometer. And the very important part in the center is a beam splitter. So the beam splitter split the light in two equal components. So 50% go up or is transmitted, and 50% is reflected and go there. And then you have two mirrors. One is fixed, it doesn't move, and the other one, which you can move. And the light is reflected back into the beam splitter. And again, you have a component that is transmitted and reflected. And you can play with the distance of this mirror and change it so that once the two beams are recombined at the beam splitter, they can start to interfere. So you can basically put them out of phase. So when the light is completely out of phase, you'll detect absolutely no light because they cancel out each other. But when they are aligned at specific position of the mirror, the two beams will be recombined and aligned there. Then you'll see full amount of light on the detector, like right here. So, so that's an interferometer, and how you use it. You move your mirror, you take an image, you move your mirror, you take an image, and then you measure those interference patterns that are called interferogram. And that's how you get information on the light. So ultimately, if you shine a light source, like just a red laser, you'll see like a sine function as a result of scanning the interferogram. If it's a green laser, it'll be the same thing, but it will oscillate a little bit faster. And if you put them together in the instrument at the same time, well, the signal will be a combination of those two. And it will be the same for a very complex light. So the interferometer allows you to measure these things. And the Fourier transform, that fancy term that I was using earlier, is what the mathematical tool that allows you to go back into the spectra and see the spectra of the light. So these are just a couple of interferograms. They look funny. They have different beatings, patterns, and stuff. They were produced artificially just to show you how they work. So this is an interferogram of two lines, the two over there. If I put 3 lines, it looks like this. And if I put 5 lines, it looks like this. And I'm really used to see those signals. It's the raw data coming out of CITEL. And after analyzing the data, this is what I get on my computer. And this is the interferogram of the first object that we observed, that M57 nebulae here. So you have the air mass of the object, of course, that changed. So it changed a little bit the look of the interferogram. This is another example of a supernova remnant. But ultimately, CITEL is also a little bit better than a simple Michelson interferometer like this, because if we had put this very interferometer in CITEL, there's one problem, because half of the light would go back into the source. There's always a reflected component and a component that is transmitted, so we would lose half of the light. So to compensate that, we tilted CITEL on the side. So it's not a 90-degree angle, it's slightly tilted. And therefore, we have 2 detectors instead of 1, and we gather all of the light coming from space. Okay. And I'm seeing the time, and I'm just going to skip a few slides so that we can, I want to talk about signal. So I'm just going to jump to, oh, wait, I'm going to show you this at least. So here is just an example of a galaxy that was observed with CITEL. So the data is spectra for all the pixels of the image. So once the data is reduced, it looks like this. I'm going to show you this video. I'm going through the wavelength, through the colors, basically, of the spectra doing that video. And you see some regions getting super bright suddenly in the galaxy. And you can see also that the lower part of the galaxy get brighter first, and then the upper part, it's like a wave. And so that's because you have an emission line, like hydrogen, for instance, that is lighting up in that very color of the spectrum. But it's also shifted a little bit to the blue or a little bit to the red because of the rotation of the galaxy. So you actually see this wave, it's due to the rotation of the galaxy. And those big flashes are different atoms that are shining in that specific color. So within that video, we saw hydrogen, nitrogen, and sulfur going through. And if you're careful, you might see flashes that are all over the field of view. Those are from the sky lines, the emission lines that are coming from our sky that we can correct for. And I can zoom in different areas and show you all these blobs that are warm gas and star forming regions. And we can even look at larger star forming regions in more detail. So within one data cube, we call them data cube, I have thousands of star forming regions I can study. And I have a lot of information about the different elements, how much light they produce, and I can study that in combination with studying the stars that are inside the region. Okay, so CITEL is the perfect tool to launch a survey. So what I did in 2018, I submitted a proposal to do a large survey with the instrument at the telescope called Signal. I'm doing this survey with 4 other co-PIs from Hawaii, France, and Canada. And the idea was to use the instrument at its best in studying galaxies that are close to the Milky Way, because it has a very large field of view, 11 arc-minute in size. And we can sample as many star-forming regions as we can with different characteristics and trying to understand why the star-forming regions are different in different environments. So it's a big collaborations. We are about 70 members now, a lot of Canadian, of course, but in 16 countries. And each of the collaborators bring their specific expertise to the survey. So some people are more studying the dynamic, the motion. Some are studying the stars. Some are studying the gas and modelizing the gas. And some people like to study larger scale, like the position of the star-forming regions within the great structures of galaxy, like bars, spiral arm, and things like that. This is a picture of our first workshop that happened in 2019. And so the whole survey will be tackling a lot of different things. So we aim at studying how fast stars are forming in different environments, how efficiently the gas can be transformed into stars. So not every region is very efficient at transforming the gas in stars. So we're trying to understand that. And also we'll be able to see for one of the first time how this stellar initial mass function, how many big stars with comparison with the small stars are, how uniform this stellar initial mass function is throughout galaxy and different environment. And what I mean by environment is in galaxies, you have galaxies that have different abundances. The small galaxies tend to be less metallic, so more hydrogen. And you tend to have also areas with more gas or less gas, and areas with more stars and less stars. So by studying the impact of the local environment close by the star-forming region, and their own characteristic, we'll see how this process is going. Okay, and I want to keep time for questions, so I'm just gonna show you. Yes, at least this was about halfway. Like last year, this was a slide that I made out of all of the data cubes that were gathered about a year ago. And you might recognize M33 here. We had to cover M33 in a mosaic. So we gathered almost, well, yeah, we finished the 9 fields to cover M33. We have a lot of spirals, a lot of irregular galaxies with different mass, small and big. And this is what the survey is about. At that time, I had 30,000 regions, but nowadays we're finishing up the analyzing the data that was gathered the last year. And this last year was one of the largest one observation-wise for the survey. So we're at about 50,000 region now. And so for each of them, we go through this analysis. We detect the warm gas components. We detect these little regions and we study them separately. And ultimately, we'll be able to study them as a population of star-forming region in different environments. So there's different tools that we can use. We can study them individually. We can look at the light, if they're spherical, irregular, or their profile, basically. We can study how much gas, diffuse gas is around them. And we are currently building a lot of tools to play with this very massive data set. One of my students is actually working on implementing some machine learning technique into identifying the region and fitting their components more quickly. But yeah, I don't want to go into too much detail of the analysis. Maybe like if you have a specific question, I could answer. And I'm gonna finish just by saying that I'm gonna come back to Canada in September. So I accepted a new position in Toronto at the University of Toronto, the Dunlap Department for Astronomy and Astrophysics. And also the Dunlap Institute for Astronomy and Astrophysics. And what I'm going to be doing there is building a lab for developing new instruments for telescopes. And I have a plan to build an instrument that is inspired by the same technology that is inside CITEL, but will be slightly different. So you might recognize those nice beam splitters, so the things that are splitting the light in two components in there. There's two of them. So very quickly, this instrument would tackle the visible light and the infrared light in two different arms. And it would use very special detectors that have been developed in the past decade and are called MKIDS detectors. So typical detectors are counting photons. You expose some patch of sky and you count photons and you have an image. So these MKIDS detector are not only counting photons, but they also are giving you a little bit of information about the energy of the photons. For each photons, you have a arrival time and an idea of their energy. So I'm going to combine this design with those detectors in order to build this imaging spectrograph that will be at much higher resolution. So that's my idea for the next probably 5 to 10 years to go. That's my estimate here on how much time it will take to develop the software to deal with this instrument. And I hope you like the presentation, that maybe you are curious about these instruments and about signals. Signal is just complete. It was just completed in the last semester. So we're ongoing. It's an ongoing analysis. And I expect a lot of things to come out of it, not only about star forming regions, but also about objects that are inside the CITEL field. So supernova remnant, planetary nebula, they are all there, and they are emitting light just like the star forming region. And so we'll be able to publish catalogs of star forming region, planetary nebula, supernova remnant, and study them in really, really large scale, like thousands of them at the same time. Which is going to be a really powerful tool for a lot of astronomers. So I hope you like the presentation, and I'll be happy to answer your question. Thanks.
Super. Thank you very much, Laurie. Yeah, thanks. Laurie, just while people think about their questions for a second, I was struck by one thing with your models, and I don't want to put weight on models that were interpreted, were intended to demonstrate one thing, but in your model for nebular star formation, I mean, it was pretty apparent, and then we went to star formations in the galaxy, and there was quite evident rotation. Does your model with the nebular star formation, do you have any notion or modeling of the angular momentum, or where that gets introduced?
Okay, so the models that I've showed, the videos are from different teams. Of course, I didn't do those models specifically. I wish I had, but yeah, those models are from different teams that are specifically doing simulation for those characteristics. And you're right, a model tends to be focused on proving one thing, demonstrating one thing, and if I include the angular momentum of an initial region of a warm cloud of gas in a galaxy into the equation, there's a couple of things. So the star forming regions tend to be located in higher density around the spiral arms. And gas doesn't flow in galaxy the same way necessarily as star. We call it viscosity in astronomy. It is there's like this kind of large scale friction between particles of gas that you don't necessarily see with stars, and shears and things like that. So if you have a cloud of gas that is going around the galaxy at a different speed, it will be compressed, and there'll be a lot of things that happens, and that's why actually there's more star forming region in the spiral arms, because you have things that happen that comes in at a certain speed. There's a higher density in the spiral arm, get compressed and form stars. But stars that are formed, depending on when this process starts, the stars, once they're formed, they're going to keep their momentum. And in some cases, especially for the massive stars, they end up going faster than the rest. And you see an offset with their position and the gas where they are formed. Because of that, most H region are not perfect sphere, but often the stars are offset on one side, and then you have a cloud on one edge. But it's not always the case. It depends on their position and their velocity and things like that. So it would be hard for me to answer your question fully because there's a lot of different cases.
Sure.
But yeah, each region, depending on where they are, as a function of the radius on the galaxy, this phenomenon affects them differently.
Okay, thank you. Anybody else at this point, or shall I just carry on with my questions?
There's some people with the hands up.
I did
See, David, yeah.
There they are. Perfect, thank you. I wasn't looking in the right place. David, you are number one. Why don't you go for it?
Sure. I've been very interested in star forming regions, and I've been imaging them all over the place because it looks analogous to fluid flow in porous media, multi-phase flow in porous media. And I imagine that the stars are blowing the gas away from them once they're formed. So is there a separation process that's going on at the same time? Like, are certain ions, do they have a bigger cross-sectional area to be hit and
There is so that's at the scale of galaxies, it is true. Like there's a phenomenon that is well known, especially when the galaxy were smaller. You had like so many star forming regions, their overall like photon pressure was pushing the atoms, and the heavier the atoms, the more likely they were to be pushed outside of the galaxy. So heavier metal tend to just go into the intergalactic medium in between galaxies. And simulation nowadays come up with numbers, how many of the metals were like pushed out. And about half of the metal in the universe are in between galaxies. They're not in galaxies actually nowadays because of that process. There's another thing, and I'm going to share screen very quickly again, because I had one slide that I didn't show that I think is also pretty cool regarding that, if I can find it. Going to be up there. Yes, this one. So I have on this slide 3 different regions. They are about the same luminosity, roughly the same size. Okay, so you have this one, and this one. The difference is how much the stellar winds affected the gas around. So how much time was for the star winds to push things around. So you can see this one is really compact, this one is intermediate, and this one is really expanded, and it's ultimately a shell in expansion. So there's also this dynamical model of evolution that goes with the regions.
Yeah, we had one, just to follow. We had for flow in porous media, there's a phenomenon called viscous fingering. So if you're trying to push something with a high viscosity with something with a low viscosity, it fingers around and moves around, and looks like it creates these globules that are sort of protected by dust or heavy where additional stars form. That's my understanding. Is that?
Yeah, so yeah, like I remember reading things regarding to this. So when you look at specific nebulae that show like the Eagle nebulae and the ones with like the finger shaped structures, it tend to be related to that. The thing is, once you have a clump that is close to the threshold to form stars, that radiative pressure really is like that little trigger that can start the process, and then it shields everything. It stays there because it has enough mass in it, and the gravity is keeping the clump together, even if the radiation is there. And so it protects this channel, and it creates those kind of finger-like looking structure.
Cool, thank you. Wonderful talk.
Thank you.
Chris, do you want to ask your question? I'm assuming you were identified as host.
I'm seeing Brock as being the second person.
Oh, Brock is okay. Brock, you were on top of Brock.
Yeah, they should be in your upper left corner.
Okay, fair enough. Go for it, Brock.
Okay, thanks. Very good, really good talk. My question, I actually was potentially going to ask some of the questions around what Dave asked, but he's already covered that. But I'm also curious about the technology. Am I right in thinking that you're basically doing the interferometry and the beam splitter with the entire image, and then making a ton of other images off of that as you adjust the interferometer, and then on a pixel by pixel basis, taking that entire time series and doing the FFT on that? Is that essentially what's done? Okay.
Yes. So each pixel has their own interprogram.
So I just have to make one of these.
Yeah, and the thing is, with CITEL, so I didn't necessarily mention that in detail, but since you're throwing the ball at me, that with CITEL, we're still using filters, like with cameras, we're filtering the light. We are using filters that are not too wide, not too small. And the idea is that with those small windows, we can sample very well their interferogram and get a really good spectra in that window. If it was too wide, we wouldn't have the spectral resolution. We wouldn't have good details. If it was too narrow, well, it wouldn't be efficient. Then why not using just a narrow band filter on an imager? But so that's the idea. And the instrument that I want to build is going to get rid of the filters. Instead, you're using this Enkin detectors that have the ability to know the energy of the photons with a very low resolution, but it will act as a way to split the lights in different orders or filters simultaneously. And so you'll have the full spectra all in once, instead of having to sample the light with different filters, with like what we do with CITEL.
Okay, thank you.
Chris, you're still showing as the top of the questions.
Yeah, we have two people who would like to ask here. So
okay,
Les,
you mentioned the importance of the stellar mass distribution function, but if you cannot resolve individual stars, are you able to observe or infer in some way from the observations what the stellar mass distribution functions are?
Yeah, thanks for that question. That's like the nut of the issue. So one of the beauty of having such a large sample, it's going to allow us to see large like trend. So how we are able to tackle this issue, which is like a very big problem and a very hard one to actually study. If you look at other studies that are trying to tackle the IMF, they are actually selecting objects that are in the Milky Way, very close by. They can see each stars, they can have a spectra of each stars, fit the spectral distribution of each star and get their mass. I'm not doing this, but I get the light emitted by the gas around them. So out of my 50,000 ASTRA regions, I have maybe half, last estimate was about half of them that are symmetrical. So they have their star in their center and the gases around them, and they are also not losing photons. All the like the high energy photons that are capable of warming the gas are absorbed locally in that gas. And because of that, I have an idea of the energy emitted by the massive stars, but not like each one of them, but them as a group. And I have 1,000, like thousands of them. So with that in hand, you can distinguish between a case where you have a slightly different IMF function, so the initial mass function. If you have a little bit more massive, very massive stars than the slightly less massive star in that group of region, I can distinguish that. So I'm using this large sample as a statistical tool to tackle this issue instead of having just one region at a time, which is then it has again another problem. If you are studying things in the Milky Way, like most people do, then you don't have a lot of data points to prove what you're saying. So is it just one case? Okay, this region has a slightly different IMF, but is it universal? Wouldn't be able to tell. But with a large sample like mine, it gives you like an idea of how much it varies. So that's our goal. At the end, I'm probably going to be able to tell you, like, yes, it varies by at least this much, but it won't be that precise yet.
Laurie, this is Randy Enkin. First of all, I'm just blown away, and I love the combination of instrumentation right through to the interpretation. Now, I've heard at the CFHT and other major facilities, changing instruments is a very big deal. And in general, they would do like megacam during the new moon, and they would do the spectroscopy during the lunar nights. And you kind of doing everything. I'm wondering, how much time do you get up there? How do they make the decision?
Yeah.
And you're the new one on the block too. And megacam, I know, is like a workhorse.
Yeah.
What's the process? I'm just fascinated that you come with this thing and say, I want some time there too.
Yeah. So the process of requesting telescope time, it goes through a series of proposal semesters. So we have a semester at the beginning of the year and then a B semester at the end of the year. So anybody can request time. And then astronomers at CFHT like me do a technical review of those proposals just to do, yeah, this is feasible. And then if it is approved by the technical team, it goes to a science team that then rank the proposal and how important they are for science advance. And then we get ranking of all the things that the people want to observe at CFHT with different instruments, different kind of constraint, like someone new moon, someone they can take a little moon, some can take a little cloud, some can't, and then they need super high image quality, some others don't. It's a very intense block of information to swallow. Our science director takes these with the ranking. He's looking at the schedule, and then of course he's going to put instruments that are looking at the visible light, like megacam and CITEL for the new moon area, and then usually the spectrographs and WIRCam, the infrared, can take a little moon, so they are around the full moon, and they're going to see what amount of time was accepted by the science committee, how much time was requested on WIRCam, how much time was requested on megacam, and then he'll try to put as many nights for each instrument as it was requested in proportion, and also optimizing the moon phases. And then on top of that, we don't do exchanges during the weekends because our team working in Hilo, they don't want to go to the 7 on Saturdays and Sundays and the holidays. And then he plays with these numbers, and we try to make it work. And at the end of the day, the system works pretty well. It's more efficient than the more classical way of observing, where you have the astronomers that come and observe their thing and then go back home. So astronomer like me, I get every semester the schedule that the director has done. I have all of the data that needs to be observed and their constraint, and I plan the nights with my team. And I do about 3 weeks over a semester, 3 to 4 weeks of planning. So I get all of the things that need to be observed, and I'm scheduling it in the most efficient way when the objects are designated and things like that. And then I validate when the data are good.
Super, thank you. I think I'm gonna go to Janine now. I think she's been waiting the longest. Go ahead, Janine.
Thanks, Jeff, and thanks, Laurie. I echo what Randy said about the scope of your presentation and your ability to be a talented explainer of these highly technical concepts that are most of which, to be honest, were beyond me. But the testimony is in the fact that you're now going to U of T to build an upgrade of all of the design and the results that you showed us. So congratulations.
Thank you.
Where does Mauna Kea Spectroscopic Explorer fit in the journey of what you've said? Is this a replacement that's going to be in U of T? And I have a second question. I don't know if you want me to ask it. It's not a technical one, or should I wait till you?
So yeah, sure, ask it. I'm gonna keep that in mind. Yeah.
Okay, so my second question is more in the culture of astronomy. At the Sky News magazine article I referred to earlier, you took the opportunity to speak about being an Indigenous person in astronomy. That really caught my attention and my respect. And I was trying to think of a broad enough question to get the most of your opinions here, but is there any guidance you would have for amateur astronomy associations? And I'm speaking from Nanaimo Astronomy because I'm not in the leadership at RASC, that could broaden the diversity. We are doing pretty good on women, and I know Margie Welchframe has done a great job at RASC Victoria, but there are many more other diversities. So if you have any comments on specifically, I guess, amateur or astronomy organizations, and in even more general than that, if you'd like.
Yeah, I can probably connect the two questions. So with the Mauna Kea Spectroscopic Explorer, it's the future of the telescope here. It's an upgrade to get to a more than a 10-meter class telescope using the same building. The idea is also to reduce the impact of the footprint of the telescope on the mountain, which is a sacred site for the Hawaiian community. And we've seen in the past what is happening when the community is not listened to and taken into account when we develop projects regarding astronomy. Astronomy is often involving the summit of the most beautiful mountains on the world. Mauna Kea is one of them, but all of them are sacred sites. And we often forget about that. And so with the Mauna Kea Spectroscopic Explorer, the last news that I had is that they're planning to get through the process of having this acceptance from the community and fund the telescope upgrade. And they want to build a very massive spectroscopy facility that has more than 20,000 optical fibers, for each of which you would have in high resolution spectra. It's a very intense telescope. It's a challenge, but I think it is a challenge for astronomy, culturally speaking, even more than it is a technical one. The thing is, since I've been working here in Hawaii, I've learned a lot of things. Hawaii has some similarities to what we have in Canada, but it also has a lot of differences. And one of the things that I have implemented with the students that I've worked with here in Hawaii is to get a cultural training before we go to the summit. So we do safety trainings and things like that for the high altitude, but even before going, I want the students to understand what is Mauna Kea and what it stands for, and how you have to behave when you're on the mountain. And it seems as if, and I see it all of the time, Mauna Kea is also a pretty touristic location. We have a lot of tourists on the mountain. If any of you have had the chance to visit, you have probably seen the hundreds of cars going up to the summit to see the sunset, and then the traffic to go down the mountain. This is a reality that the community here have to deal with. And not only the road has brought that to them, but astronomy in general. And those tourists are not necessarily behaving the way you should behave on a sacred site. So regarding your other questions for astronomy amateur groups to be more representative and to change behavior, there's another presentation that I gave about how to indigenize astronomy, and I think it's really relevant to that. Some of the key points that I think are really important is to transform your presentation when you're giving presentations to groups that are located close to one of the community. You can try to include some of their respective astronomical knowledge into your presentation. Try to learn beforehand from them, and include that into your presentation. I think that is a little bit of effort that needs to be done, of course, but it's something that is really rewarding. I've been doing that, especially with an initiative that is called Connected North, where I get connected to classes across Canada and talk to students in classrooms, mostly in remote localities. And I tried to gather that information. It's not easy. And with time, I got better and I got more information and I got more contact and more people I can exchange with. And this network now makes me feel more comfortable talking about it. And I'm sure you guys are around Victoria. You have multiple communities in which you live with and that you can talk to. You can also learn a little bit from their language. I've learned from all the native language, and including mine, the Innu language, by understanding a few words like what is the sun, what is the moon, what is the word used for those very simple objects in the sky. Sometimes it gives you a glimpse about their own understanding of the sky and their own vision of the sky, and it's a little bit of of things that can help you connect with them. And I think it's one of the first steps that has to be done. And hopefully, by doing that, it's gonna just grow, into a bigger network, maybe more including more members eventually. But yeah, I appreciate that you answered that, that you asked that question, because without doing that effort, this inclusivity is never going to happen by itself. So there is definitely that.
Well, I'm going to have my people call your people about that indigeneity.
Yes, yeah.
Thank you.
Chris, I'll go back to the boardroom.
Yeah, one more, Rich here.
Laurie, thanks for this lovely talk. It seems to me that CITEL is a very exotic and leading edge instrument. Is this type of technology being pioneered or explored at other institutes as well, or other observatories?
Yeah, it is a technology that ultimately was used before, but mostly in the infrared or even larger wavelengths. So you might have heard of Herschel, Spire, Spire space instruments, and they were using Fourier transform spectroscopy. But the technicality with CITEL is to push it to the close to UV light. So the smaller the wavelength, the smaller the more precise the instrument has to be. So if you're trying to sample the blue light, which oscillate very fast, your mirror positioning system has to be very accurate and very it is also very sensitive to vibration and earthquakes. And so that was the challenge with CITEL. All the optical parts, in the instrument were challenging to be developed for this band of light. So having a good detector is one thing. Having the most perfect beam splitter that splits the light in 50-50 for all of the wavelengths of your instrument is also something very challenging. And if you get all of these ingredients together and you're able to develop an instrument like that, there's still a lot of development in software that is completely isolated from most instruments. So the software to analyze the data for CITEL is very different. So it was not necessarily something that was completely new, but a lot of it is new. And I still believe that it is a very interesting design. One of the main, well, I mentioned CITEL has a very large field of view for a spectroscope, like an imaging spectrograph. It is very rare. Most imaging spectrograph are very small with other technologies. And on top of that, what we call the throughput, the amount of light that at the end gets on your detector from the sky to the detector, you lose a lot of photons on the way from mirrors, reflection, filters, name it. The throughput of these instruments can be very high. So CITEL is about 60%. A typical high resolution spectrograph like Spiru is, I think, 10%. Espadon is like 15 or something like that. So 60% of throughput, it means more light that you detect and you can do science with. And I believe that we can go all the way up to 80% with just improving the technologies and improving all the parts. And you will never be able to do that with a traditional spectrograph.
You also mentioned near the beginning that you could actually use, I think you called it a light pipe, I guess fiber optics to direct light from Gemini North to the CITEL system, and that kind of blew my mind. Is that?
Yeah, to Espadon. Yeah, not to CITEL, but to Espadon. So it's the light from one star, of course. Yeah, it would be hard to, yeah, it would be hard to do the full image. Not impossible, but very hard.
That makes me feel better. Thank you.
Are there any other questions that anybody wants to raise with Laurie?
Laurie had typed one. It's in the chat, Jeff. I don't know if you want to read it.
Laurie Roche. Oh, yes. Okay. Laurie, I wasn't sure that was intended to be read here. So there's a question just on the question board here, Laurie.
Yep. Yeah, I see that. So if there's already a location for that hypothetical instrument, no, there is none. So one of the beauty of research and development is, and also the freedom that I have as a researcher to be working in a development lab, is to push an idea further. My goal in developing this prototype in lab is to be able to show people that this technology works and that I can combine it with this special detector and make it even better in order to interest people to that very design. After that, the prototype that I will be building, if everything goes well and we can demonstrate its power, we can then apply for government money in collaboration with telescopes in order to build the real thing, to build an instrument that it will be dedicated for a specific telescope. So my prototype will be an in-lab instrument. And then the instrument that would be for a telescope would be probably built much later and at much larger scale with a very, a partner in mind and a telescope in mind. It would have to be for a large aperture telescope. The very reason for that is if you have ever seen those designs for telescope, like the quadrimirror of the LSST, I don't know if you've ever seen those. So there's multiple reflection that happens, and the instruments are located on the side of the telescope. They're not on the telescope itself at the top or the bottom. They're on a platform. And my instrument will have to be on a platform to deal with control of vibration. And the detectors that I will be using are cooled at almost 0 Kelvin. It's about 100 millikelvin in temperature, and they have compressors that have that induce a lot of vibration. So they have to be decoupled from the instrument. So it would be impossible to put that on a telescope. It would have to be on a platform on a large aperture telescope like this.
Thank you. I have one other question, if I could.
Go ahead.
Is there any work being done right now at the DAO that is being used by your group or has been used by your group? I'm thinking of the technology team that's doing an awful lot of work up at the DAO. Are you using any of that, or is it coming online?
Yeah, so there are some cross section. Every development that is done in Canada, especially in spectroscopy, we're good in spectroscopy. We've inherited from the Heisenberg legacy, and so spectroscopy has been something in Canada and multiple areas, and astronomy is one of them. And what is developed in Victoria, and I have collaborators over there. You have systems for controlling corrections of the aperture of the telescope, so the adaptive optics. So when you have a telescope, and of course the atmosphere above the telescope is kind of perturbating the light coming from the stars, and so we have those very well-developed systems to correct for that, especially for very large aperture telescope. And then we have so the fact that we have this knowledge on spectroscopy, when we develop high-end product like CITEL or this instrument that I want to develop, it's also easier to find people to work with you locally. And even though they haven't necessarily worked exactly on the same instrument as you, or they don't have necessarily they have built exactly the part that you need, their knowledge base is just extremely related to it, because it's spectroscopy at the end. And so that is very valuable. And so we are in really good position in Canada for developing instrumentation in astronomy for a country that is much smaller than the US or others that, you know, are playing this game. So yeah, we're really doing good.
Thank you.
Miles, you got a question? I think you muted there, Miles.
How did you get involved in this? Were you an astronomer at the age of 3?
No. So that's a funny thing. I've always loved to look at the stars. So my family was always outdoor the long summer, you know. And you know, the thing is, I remember from being very, very young, just looking at the Perseid, or my dad just waking me up at midnight because there was auroras. And I know that I was asking a lot of questions. My dad remembers them, and I'm stunned by the kind of questions I was putting him through when I was super young, because he had to find an answer that I could understand, and even sometimes he didn't know. And he always said I was going to be an astronaut, and I didn't fall too far away from his idea. But I always tell people I didn't know when I was young I could be an astronomer. That's the thing. It came up really later in my career, probably when I was doing physics at the university, that then I saw the possibility of being an astronomer, which is pretty late when you think about it. I knew I was a scientist. I was very inquisitive, and physics was for me a challenge, and I really enjoyed it. So after doing a bachelor degree in physics, it was then obvious that I had to do astronomy because of everything that had happened in my life. So I should have known that I was going to be an astronomer, but it took me a while to realize it. Yeah.
Okay. Well, thank you very much for a very comprehensive talk. Your enthusiasm is just wonderful to experience. Really appreciate it.
Yeah, my pleasure. If you have any other questions, you can find me online and just send me an email. I'll be happy to answer it.
Thanks very much. We've got
Thank you, Laurie.
Okay.
two
Bye.
Bye, Laurie.
Thank you.
Two other items just wanted to touch on. Firstly, with Jim Hesser. Several weeks ago, I mentioned that the rehabilitated Langham Theatre was producing the play Silent Sky, late January, early February. Jim has sent around a little note about his participation in that. He was actually asked to be the technical advisor back in 2020 when the play originally came to the Langham Theater, which was canceled because of COVID. It's been resurrected, and he's again the technical director, the scientific advisor for the play. So I just asked him about his involvement there and about the play, and he wrote quite an interesting little précis that was sent around to everybody probably 3 or 4 days ago. Jim, is there anything you'd like to say, or do you want to just quickly run through your involvement with that play? And certainly, if there are any questions anybody has about that or about the play, Jim will offered that he would try to answer.
Well, thank you, Jeff. I haven't prepared anything although just to follow up on Laurie's amazing talk that we all so enjoyed. The light pipe between Gemini North and CFHT was developed at DAO, John Pazzer. So there's another connection to the interrelationship between our instrumentation development activities here in Victoria and CFHT. The wife of a retired astronomer at the observatories lamentably passed away a number of years ago, Stephen Morris. Her career was spent in theater in Victoria. And when the idea of Langham Court doing Silent Sky came up, she volunteered me to serve as somebody who can answer questions that the production team and the actors might have. And it's just been an awful lot of fun to be involved with it. It's an amazing group of very, very dedicated people who are not being paid. I mean, that's a pretty volunteer organization. And so I had it's something I've been, as a result of this, I realized that my career has been during the transition from the types of techniques that were in use in the early 20th century when Henrietta Leavitt was at Harvard doing her work on the Harvard plates and the modern detectors. And so I took a lot of photographic plates when I was working in Chile in the 60s and 70s. And I was able to take, real astronomical photographic plates to their rehearsals and let them see what sort of material Henrietta Leavitt was working with. And I borrowed from the DAO library a bound volume of publications from her era. And it was an absolute hoot when I opened that to a page of Henrietta Leavitt's research, one of her research papers. And the woman who's playing her in the play just took immediate ownership. Those are my papers. It was really fun. I mean, these actors really are into it. And I have watched rehearsal. I think it's going to be a wonderful performance. Some of you may have seen in Chemainus 5 or 6 years ago, a group there put on Silent Sky. Unfortunately, I wasn't able to, Betty and I weren't able to attend, but I think there are some wonderful lessons in this play that members of the RASC will very much enjoy if you're able to get to a performance. And my role has been, I did attend lots of meetings and so on, but my role has been very, very modest. Sarah Ellison, who is giving a presentation after the February 5th matinee performance, she gave this presentation to the original actors in early 2020. And it's a wonderful presentation, and in it she brings up the situation facing women in astronomy then and now and the many changes that have taken place. So for people who are able to attend that particular performance, I can guarantee they will hear a wonderful presentation on galaxies, followed by discussion on how things have changed for women and perhaps generally minorities in astronomy today. So I'd be willing to try to answer any questions, but I think my main message was this is a wonderful opportunity. The actors are good. I think people, particularly people with the interest of rascals, will really enjoy it. And I just urge you to support them. Go out and enjoy yourself.
Thank you, Jim. I appreciate your comments, given that I put you on the spot suddenly. Are there any questions that anybody has about the production or about Jim's role?
Question from us.
Yes.
Yeah, as a science advisor, is this an adaptation of the original play, or is this verbatim of what the original, I believe it was written in 2015 or something, or?
No, it's the original play. Absolutely.
So what do you do as an advisor then?
Well, it was trying to explain,
To the
most
actor?
people, I mean, most people today, the only camera they know about is a CCD inside their cell phone, right? So showing people a real glass photograph and that you could write on one side of it, but not the other, and you handle it by the edges and they break if you drop it, etc. That's sort of just sharing the experience of what it was like as an astronomer to use the same type of equipment that was used when the photographic process and the plates developed in the late 1800s. And if they had specific questions, I would try to answer. But again, in many ways, Sarah put it all in perspective with the beautiful talk she gave the original cast. The cast is only 5 people, and 2 of the original cast weren't able to continue with the production this winter. I don't know why, but the woman who is the actor who is playing Henrietta Leavitt, she was extremely ready to go in 2020. When COVID closed everything down, the production was going to start about in late April, as I recall. So she knew her role, and she still knows her role. At a rehearsal 10 days ago, she once again brought tears to my eyes. So the story is quite powerful.
One of the things that blew my mind in reading Glass Universe was just the absolute precision and the almost mind-bending care that had to be taken with these plates and this tiny reticule that she developed to measure and differentiate the stars, and then have to repeat that day after day to see the variation.
Yes, yeah, no, they worked extremely hard, and they were very lowly paid. So,
One more question, Jeff.
Jim, Randy
Yeah.
here.
Go ahead.
So one thing, does the play talk about the fly spankers?
The fly spankers are mentioned in the play, yes.
Because I just love that concept. I was reading about it just yesterday. But I also was looking at Leavitt's original graph, which was a log plot from a day period to 120 days. Do you know, I haven't found the information about how often the magellanic clouds were photographed, that she was able to pull off periods off all those stars.
I don't know the exact cadence, but they were regularly observed at the the Boyden station. So she had the material with which to derive their periods, which was absolutely critical. And something that many people may not appreciate, the Hubble Space Telescope, one of the most important arguments that astronomers made in the 60s and 70s, get the funding for Hubble, was to extend the study of Cepheids to the Virgo cluster of galaxies, and thereby move the whole, our knowledge of accurate distance, period luminosity relation out to much greater distances in the universe. And so really extended the distance ladder. And it's all based upon this beautiful work that she did a century ago. Yeah, it's really a cool story of human. It's a cool story of human curiosity, which we just heard in spades from Laurie in her talk. And so yeah, it's a very powerful dramatization of it all, because Henrietta Leavitt had serious medical problems in her life, and yeah, but she just did something quite amazing, and it's celebrated in this play.
Thank you, Jim.
You're welcome.
There was one other note that I have here that we wanted to talk about, the conjunction of Venus.
Yeah, Randy wanted to speak, so.
Randy, okay, awesome.
Okay, well, so I'm actually going to say two things. One, as you know, I'm quite passionate about my astronomy, but in my daily life, I'm an earth scientist. And on Wednesday at 2 o'clock, I am going to have an extended live cast on YouTube with Professor Nick Zentner from Central Washington University on a topic that was near and dear to my heart. I wrote a review paper in 2006 and I haven't touched it since, but he's doing a 26 show deep dive into a controversy called Baja BC, but about how the Canadian or the North American Cordillera was formed. And so I'll send around a link, but it will be on YouTube for perpetuity afterwards. And I've been having a great time watching all the other interviews up to now. It's called Baja BC A to Z. He's American, and I'll be Q. Each lecture has been given the next letter of the alphabet, and I think it's really cool. But back to astronomy, everybody has their observer's handbook, I am sure. And just want to tell you, first of all, when you go in the sky month by month, they put in bold under the events, the things that you can see each month, which are really quite impressive for any matter. But on the 22nd, Sunday the 22nd at 20 UT, so that means it's going to be in our afternoon. So it's really on the 21st and the 22nd. Venus is less than half a degree from Saturn. You're going to be able to see in your binocular, but just by naked eye, they're going to be right on top of each other. If we ever get any clear skies this week, take a look just after the sun goes down and watch Saturn, which will be coming down from higher in the sky, Venus moving up from lower in the sky, and they're going to come together on Sunday. And I remember very well, was it 2 years ago when Jupiter and Saturn crossed, and it was really fun tracking that day by day until they hit. So we've got another one As long as they give us clear skies, Reg.
We're working on it.
So just after sundown each day, so early evening. Because Venus is going to set, I forget what time. Do you know, Bill?
I'm not sure if we heard you.
I was looking up in Stellarium to try and figure it out. So, I don't know. I mean, you should be able to see it before, well, you should see Venus before sunset.
Yeah, yeah. And then as soon as it gets dark enough, then you'll see that. I find Saturn, you can see even light polluted sky. It is one of the first points of light in the sky after Jupiter and Venus. Saturn's one of them. And it should be really nice in binoculars. Is there anything else this week? Not really. New moon is on the 21st. Now, there is actually on the 29th, Uranus is occulted by the moon. And when was it? It was a few months ago, there was a Uranus moon occultation, which a lot of us watched. It was in the evening. This one is at 4. So that's going to be at 8 o'clock on Sunday. Well, no, that would be on Saturday, 28th. Because of this being UT. So Saturday on the 28th, that was really fun trying to actually time when Uranus went under. And I know David watched it, Nathan watched it, I'm not sure who else, but it was pretty fun to watch. But I'm going to, if it pleases the crowd, I think we should pull out the Observer's Handbook and just know what are the really cool things coming up in the coming week or two. So I'm going to see if I can remember to do that.
Is this comet beginning of February? Possibly visible?
It's visible now, isn't it? If you're
Visible
if you're
now?
up, yeah, if you're up at night, yes, the wee hours.
Wee hours and it's past the perihelion, I believe. I think it's on.
It's
coming up the other
closest in the beginning of February, but you can see
Yeah.
visually with your eyes?
Sherry saw it with binoculars, and
Yeah,
that he posted
it's
that.
fifth magnitude, so it depends on how bright the sky is. If the moon's out, you'll need binoculars, but
Yeah.
if not, you might see it naked eye.
So it's naked eye in beginning of when it closest approach.
It's zipping by Polaris. So it's.
Oh.
Oh, man.
It is.
That's pretty cool. Conjunction.
Has anybody else seen the comet?
I saw it 10 days ago. I can't remember what date it was now. I think it was the 5th in the middle of the night.
Yeah, I tried, but it was unfortunate, the location. It was quite low to the horizon, and I wasn't willing to stay up much later. I probably should have acted earlier. Maybe this is a word to other people that try to observe this. When the sky is clear, and if it's really low the horizon, you should get to a place where you can see it, because unfortunately I banked on it being clear when it had risen, which it didn't.
It's not going to be a neowise.
No.
No, I don't know. I don't think so.
Magnitude 5, isn't it?
Yeah.
That's what it is now, yeah.
I think it should be good if you're a kind of a 6 o'clock waker upper. I think that's a pretty reasonable, it'll be nice and high if there's ever a clear sky.
Yep. Yeah, I think optimally, I figured maybe around 3 is a good time. You know, if you stay up late, that's not too bad. If you get up early, that's not too bad. So it's somewhere in the middle.
So when is it close to Polaris? I think around January 27th, something like that.
Yeah, near the end of the month.
And is it that it's getting brighter or is it already dimming?
Who knows? It's a comet.
Yeah.
They do what they want. It's a stubby little comet. If you've looked at images that are highly processed, it shows this fabulous iron tail. But if you look at the tail that we see, it's a stubby little thing.
It's quite flared. Like if you the ones that I've seen, you see the coma and then it flares out. Like it's not one of these things with a very pronounced tail. I'll try to get an image of it next time if it's clear. I'll see if we can get at least the shape of it.
Any other comments, any other things that anybody wants to bring up with the meeting this week?
Just a quick announcement, if you don't mind, for the SIG. There's a makers SIG this Thursday, just so that people know. Jim, I don't know if it's 7 or 7:30. Maybe you can, if you're still online, Jim, maybe you can tell. If you're interested, just let me know or let Jim know. I'm David at victoria.rasc.ca, and we'll let you know. We'll send you a note.
Okay.
And Laurie had something?
Good.
You're muted, Laurie.
Okay, I just wanted to let people know that I have some copies of the 2023 Almanac. I have about 4 of them, if anybody would like one. They cost $10. I think they're $10 a piece. I also have got Explore the Moon and Explore the, sorry, I've got in the wrong way here. Explore the Universe and Explore the Moon. And I know, Randy, you have asked for those too, and I've got copies of those for you. And I also have got 2 more calendars, two that are left. So if anybody would like them, you have to kind of get me like right now. And that's it.
What's the almanac?
What's the almanac?
Yeah, could you hold it up again?
Yes. This is the 2023 Night Sky Almanac that was done by Nicole Mortellero, and it goes through month by month and gives what's going to be happening. Just if I could get it, like for March, for instance, it'll give. It's kind of a little bit like the Observer's Handbook. It gives a whole bunch of information about what you can see, the moon phases, and then gives some nice pictures of the constellations, and just very succinct for in a month, like within about 4 pages for each month. It gives what you can look for each month, and so you can kind of look it up and have an idea. So it's just a nice, a very condensed version, and you don't have to look up through as much of the Observer's Handbook as you can do for this one. So.
Yeah, I can certainly vouch for that. I've been using it for a couple of years now, and it's an excellent summary. I think Laurie probably showed the page which it has a listing of all the objects, which I find really invaluable. And if people want to plan ahead, you really kind of do have to plan ahead. So what I do is the month before, I usually just go through the list and see what seems viable, and I'll plunk them actually into my phone calendar, just so that I'm reminded as to when they are. And often they require some level of planning in terms of detail. You kind of have to know what your strategy is. Like if it's something's visible in the early evening going into morning, then you have to do a little bit of planning around that. And also knowing the object, you can also look for site specific kind of information. The other thing is, like many of us probably have limited views where we live. I try to do as much as I can just from my home, but often if there's a low horizon and it's a particularly like a westerly view, I'm totally done for, because I have really tall trees in the west where I live, and so I have to go somewhere else for that anyways. But yeah, you start to develop that kind of planning helps you. You probably have favorite sites, and I do. So I know when I need a certain kind of ordinal direction for the horizon. So yeah, it's good. It's an excellent resource.
Is it a product of RASC or who puts it out?
Yes.
Yes.
Yeah, it's a RASC publication. But yeah, it's been produced for the last, I don't know, 3 years, I guess. Two or three.
It might have been 2021. There might have been a 2021 was the first
I
one.
think this is the
So
third.
this is 2023.
I think this is the
Nicole,
third version.
Nicole is the journal editor.
Yeah.
Okay.
Nicole Mortellero.
And CBC announcer and
Yes.
reporter. Yeah.
How's the road to the observatory going, Laurie?
I haven't been up because you can't really get up there. Some of the people are working up at the hill now, so there is some access, very, very limited access to the hill. They're trying to keep as many people away so that the contractors can just get to work and not have to work around them. I am going to say that we think the road should probably be done with gravel by the end of February or early March, and then will be is supposed to be paved in March sometime, maybe, or possibly early April. So we are looking forward to having it back open again in the April time is what we're looking at. So meanwhile, we're going out to the schools and and kind of they're not coming to us. We're going out to the schools right now. So that's what Calvin and I are doing. Yeah. Oh. I'll keep you informed. Yeah.
Is there anything else that anybody wants to raise? Okay, thank you. It's been a very pleasant meeting. So I will have an Astro Cafe again next week.
Thanks, Jeff.
Thank you.